Okay, so we have been discussing ordinary differential equations. We have seen the prescription for solving a linear uh, first order differential equation. We also discussed how when an equation is exact and the concept of an integrating factor, right? So sometimes an equation is not exact, but it's possible to find a factor, multiplying this equation throughout with this factor renders it exact, and once it is exact it is easy to solve it, right? So let us revisit linear first order ODEs, and use our uh, knowledge of integrating factors. That's the subject matter for this lecture. Okay, so the most general first order linear ODE is of this form: dy by dx plus p of x times y is equal to q of x, right? So suppose we want to find an integrating factor for this differential equation. So what it means is we want to be able to multiply by some function alpha of x throughout, and so the left hand side must become an exact differential, right? So we'll also explore the specific possibility of the left hand side being converted to a form where it can be written as d by dx of alpha times y, right? I mean, it's a guess that we're doing. So dy by dx is there, and then is it possible to multiply by alpha such that basically the left hand side is the same as d by dx of alpha times y, right? And if we ask for this, right, so it turns out, I mean, we have to just expand this and compare the left hand sides of these two equations, and then we immediately see that this would be possible if we choose our alpha such that d alpha by dx is equal to alpha times p, right? So we see that this equation, the first term is dy by dx. It's as if you're treating alpha as like a constant, and then the second part is where the derivative with respect to alpha comes in, and then y is treated as if it's a constant, right? So that part, if this factor alpha times p is exactly equal to d alpha by dx, then indeed this will hold, right? So we must solve for an alpha such that this condition holds. But a moment's thought reveals that in fact this is an easy differential equation. We know how to solve this. This is a separable differential equation. So we just bring alpha to the left side, and then you have dx goes to the right side, so you integrate, right? At least in principle we know how to solve this. So you have log of alpha is equal to integral of p dx, and then alpha is equal to e to the integral of p of x dx, right? So this is nothing but the integrating. So once we have the integrating factor, we can go ahead and write it, alpha of x times y is equal to integral of alpha times q, right, dx, and then we can write down what y itself is, right? So this is, if you compare notes with the earlier lecture where we worked out the solution for the 1D for the first order linear differential equation, you'll see that in fact you get exactly the same answer as before from this method. But this is just, it's illuminating to think about this in terms of an integrating factor and finding a solution for this integrating factor of this particular form. So there is another way of thinking about this, and that is the so-called variation of the constant, right, which effectively boils down to the same method that we used to first find a solution for the problem, right? So that's, again, let's start with the homogeneous equation. So we have dy by dx plus p of x times y equal to 0, right? So we know how to solve for this, right? This is a separable equation. We solve for y, and we simply have y of x is equal to a times e to the minus integral p of x dx. So this gives us a free constant a. Now using this, we want to be able to find the solution for the full inhomogeneous equation, right? So the technique of this variation of constant says that you elevate this constant to a function, right? So I mean, it's essentially what we did earlier, but I'm just putting it in somewhat different language, and then we'll just recover this. It's just you can think of it as a a revisiting exercise Alright, so the technique of variation of constant is to just write y of x as a of x times e to the minus integral p of x dx, and now this is taken to be an ansatz, right? So an ansatz is a guess that you make for a solution of your this differential equation. It's an educated guess. So given that this is a solution for the homogeneous equation, so we make the guess that y of x is equal to a of x times e to the minus integral p of x dx will be a solution to the inhomogeneous equation, right? So what should this function a of x be such that this is it possible to find such a function? And then if you demand this to be a solution of the inhomogeneous equation, we find that dA by dx must be equal to q of x. So this is now simply a matter of writing dy by dx plus p of x times y is equal to q of x and then plugging it in, right? So if you just plug this into here, you will see that e to the minus integral p of x dx comes out. So the first part will be dA by dx into this, and then there's going to be this cancellation, and so you're left with dA by dx is equal to q of x times e to the integral p of x dx, right? So this is it actually appears on the left hand side with the minus sign, and then you bring it to the right hand side, and there are these two other terms which just can get cancelled out. When you take a derivative with respect to x, if you treat a of x as a constant, there's no derivative, then you get minus p of x times a of x e to the minus integral p dx, which is the same as minus p times y, which cancels with this. So basically you're left with just this equation, dA by dx is equal to q times e to the integral p of x dx, right? So this is an equation we can solve for a, right? So a is now, it's just you have to integrate. So it's this integral of integral dx q of x times e to the integral p of x dx plus c, right? So thus we see that this is exactly the same solution that we obtained earlier, right? So y is given to be integral q of x e to the I dx plus c, the whole this entire thing times e to the minus I, where I is integral p of x dx, right? So this is in fact the same as the first method that we adopted. It's just useful to look at the same problem from many different angles and see that they all come together in a nice way, so that our understanding of the theory behind this is solidified, right? So it's in this invoking this philosophy, we have taken another look at the first order linear differential equation in this lecture. Okay, thank you.